Good morning, welcome back. I see that you still have some stamina. Okay. So are there questions about last lecture, first of all? Any questions? So during the last lecture, we described what is the peeling exploration, a deterministic peeling exploration of a planar map. And we saw that these peeling explorations, so they depend on an algorithm that we called A to explore the map edges after edges. And we saw that if the map itself is a random map sampled according to this Boltzmann measure when you fix the length of the boundary, so this PL, then this exploration was nothing but a Markov chain with explicit transition probabilities depending on these numbers W, L that we computed, kind of computed. And voila. And so today, what I want to do first is to talk about peeling exploration with target, which is the version that we will most be dealing with in the rest of the course. So it's the same setup as yesterday. You have a map. You have a map with a boundary, so an external face. And you see, again, this map as the map of the castle you are exploring. And now you have a target face. So the target face is the coffee room, let's say. And let's pretend here that the target face is this one. That's the room you want to find. So this map with my notation is an element of map with the boundary size 9, half perimeter 9 on the external face, and the target face has perimeter 4, so I put a 2 here. And again, our goal is to explore this castle by, so you imagine that this red dot is your starting point. So what do you see when you start in this castle? You see actually a room which has perimeter 18. And you're here. And you've got your root edge here. And your algorithm tells you, it was in orange yesterday, tells you, oh, I want to explore that door. Let's say, yes, let's.
The other way?
The external face is always the face on the right of the root edge.
Okay, sorry.
So, and with the same color as yesterday, this is blue because it is the unexplored region. This is a hole that I have not explored. Okay, and let's pretend my algorithm wants to explore, let's say, this edge. I want to explore this edge. So I'm in my castle, and I go here, and I open that door. So if I open that door, I enter that room. And so this was what we called yesterday the occurrence of an event of type C2 here, because we discover a new room. We discover a new room with perimeter 4. Remember that? It was the event C2. Okay, so you may then want to explore a new edge, let's say this one. So your algorithm picks this edge now. So what will I get? I will enter that room. And now what will happen here on this picture is I will again have an event of type C2. And I have a new room here. Okay? We all good? Of perimeter 4. So we have another event C2. So that's for the first one, that's the second one. Now let's complicate it a little bit. Assume now that my algorithm wants to go through that door. I want to open that door. So if I open that door in my castle, oh, I come back here in the same room. So on this picture, this is a bit more complicated to see what is going on. But let me redraw this that way. So the root edge is here. I've got this big boundary there. My two faces which I have already discovered here and there. And I have something like that. And here I have something with perimeter 1, 2, 3, 4. And so I want to, what we said yesterday, I want to peel that edge, right? And if I peel that edge, so far the explored boundary is this guy in blue. Yep. Sorry, thanks. What's the easiest way to, let me push this one. Ah, that's too bad. Oh no, that's bad. Okay, thanks. The rooted is here. That's blue here. That's a terrible pedagogical mistake. Okay, and I want to peel this one. So if I do so, I will face an event that we called yesterday an event of type G, where we split the hole into two parts by gluing these two edges together, and the hole I'm creating on the left-hand side will have perimeter 4, whereas the hole that I will leave on the right-hand side will have perimeter 12. Thanks. I keep. Are you sure?
No. 18 minus 6 12.
No, but 18 was plus 2 plus 2. So 22 minus 2 minus 4, 16. Pascal. You just lost a bottle of wine. Okay, so this was an event that we denoted by G28. Okay? But that was yesterday. But now we are targeting the coffee room here. And in this new setup with target, when I split the hole in two, there is somebody, the head of the castle, which tells you in which of these two holes is the coffee room. So in this case, you know that the coffee room is not here in that part, that the coffee room is here, right? Because the coffee room is this target face. And so that was the former step in the general peeling, but now in this peeling with target, this will be an event like that. So far the same thing. I'm drawing exactly the same thing. But the difference here is that I discover, let me complicate it a bit, the drawing here, up, something like that. So when I have an event like that, which disconnects my castle into two regions, then the one not containing the target face, the one not containing the target face, will be totally revealed for you, for free, totally revealed. And so now I know without exploring that part, without opening any door, that this is actually this. Okay? For free. When you split in two, the guy tell you, oh, don't look for that part. The coffee room is not here. Just concentrate on that part. Okay? So in the filled, so I will call that the filled-in version of the peeling process. Of the peeling process with algorithm A. So the algorithm with algo A. So the algorithm is, as usual, the deterministic function given what you have explored that tells you which edge you want to peel. So in the filled-in version of the peeling process, we fill in the regions, the holes, let's say, the holes, which do not contain the target face. All right? Is that clear? And so this event now, before on the peeling of yesterday, this hole that was a hole was split into two holes, one of perimeter 16, one of perimeter 4. In this new version, I only have a single hole after this step. And so by easy induction, on the fielding version of the pinning process, I only have a single hole for all time. Single hole. Is that clear? And I will denote this event instead of G2, 8. I will just denote this event G2 with a star, the star being saying that that's the hole I want to concentrate on. So in this pinning step, I was pinning that edge. I was leaving on the left-hand side a hole of perimeter 4, which hence these two. And I will concentrate on the hole of perimeter whatever, what it has to be, which is on my right. Okay? So I have similarly events which I will denote G star K, which are events where I disconnect a hole by leaving a part of perimeter 2K on my right and concentrate on the left-hand side. Okay? Is that clear? So when I do that, so if M is a map, deterministic map, if A is an algorithm, a pinning algorithm, what I can do is consider the filled-in pinning exploration. And this filled-in pinning exploration will always be denoted by E0, E1, En, and so on and so forth. And the difference with yesterday is here I put a bar. The bar means that I fill in all the holes that do not contain the target face. So these guys, they are submaps of N with a single hole. The hole is, again, a distinguished face with a simple boundary. Distinguished face with simple boundary. All right? Pop up. And OK, so there is a difference with the general pinning of yesterday, is that at some point we will discover the target face, right? So at some point we are facing a hole. My explored map is somewhere here, my root edge here. That's my single hole. My pinning exploration wants to peel that edge. I want to enter that door. For example, when I'm here, imagine I want to perform these pinning steps. I want to enter that room, which in this picture is peeling that edge. Okay, if I do so, what do I discover? I discover a face, which is a quadrangle. And this face is the distinguished one, so in green. Okay? That's the coffee room. I'm happy. I found it. Okay? So this event will be denoted by CK. So here K is equal to 2. It's a center event. And I will put a little stop on top of it, which tells you, OK, that's done for me. I've discovered the target face, and I stop. OK? That's my stopping rule for the pinning process. Is that clear? And then we stop. So this, in the exercise session of this afternoon, we will practice this a little bit and perform a few filled-in or not filled-in exploration of maps. OK, questions about that? So, yep?
So when you fill in the holes, like you know they're not in the space, will you like use Markov properties?
So far, this is just deterministic. There are no randomness involved. So the deterministic, the owner of the castle tells you when you split in two, no, don't go there. I give you the map of this, of that hole. You don't need to open the doors. I give it for free to you. Concentrate on the other hole. So totally deterministic. Yes?
But now when the sequence of C's and G's do not describe the exploration anymore.
No, yes, very good point. Yes. I need to tell you what are in the holes. Yes, very good point.
It was the same question.
OK, good. So now, Now, one remark. Remember that D star En, what was this? This is the half perimeter of the single hole. Okay? So now what we will do is we will concentrate on random maps. But before that, let me recap the 3 types of event I can face. So again, I've got a unique hole. Say that this hole has perimeter 2L. If I'm peeling an edge like this, there are 3 types of events that could appear. Either I'm discovering a new face, or I'm splitting my hole into 2 holes. One of them will be filled, or the face I'm discovering, let me put an hexagon here, or the face I'm discovering is actually the target face. Okay, that's exactly the 3 types of events I can face during this exploration. Okay? And when it's filled, let me put hatch. Here it's filled in. Okay, so if this has boundary size 2p, this, let me put a 2p here and a 2p here. This is the event CP. This is the event G. You need to concentrate on the left-hand side, so it's a star P. And this is CP stop. All right? Again, as yesterday, P could be equal to 0. P could be equal to 0, meaning that in this case, I'm identifying this edge with the edge immediately on its right. I'm gluing those 2 together. And so there is no guy here. P is equal to 0, meaning that I have discovered a vertex. So if P is equal to 0, that means that I have this picture, and this guy is a vertex. Okay? All right. So now let's do the same as yesterday. We focus on random maps. Okay. So let's focus on Boltzmann maps. So remember the notation PLQ. What is this? This is a distribution on maps with external face perimeter 2L, target face perimeter 2P, obtained by normalizing the Boltzmann weight, Boltzmann measure WQ. And remember that the normalizing weight, the normalizing constant, was denoted by WLP. And this guy is finite if Q is admissible. Okay? And a map sample according to this distribution, I will usually denote it by capital M, L, P. That's coherent notation, you will notice. Okay, so here is the proposition, very similar as yesterday. Proposition, so you fix L and P larger than 1. You fix an algorithm A, and you consider the filled-in peeling E0 blah 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 En of M under PLQ. Okay? Then this guy is actually a Markov chain. and you can guess the probability transition. So let me put it informally that way. So it's a Markov chain. So if I give, okay. Yeah, I will write informally that way. You will understand, let's hope. Probability to see an event ck at step n will be probability, it's qk, w, the perimeter that I'm currently exploring, plus p plus k minus 1 with the target p divided by my current perimeter. Okay. Target p, right? The probability to see the event gk1, gk2 is equal to, okay, sorry, g star k is equal to w k, w, okay, that's w, the current perimeter minus k minus 1 p divided by wp, my current perimeter. Right? And last case, probability to see the event ck stop is equal to let me put it that way, qk, and then I always start from this wen star, p, and here I need to put a wen star plus k minus 1, and let me put a p, and let me erase them in red to be sure that they are not here, no p and no qk. Okay, so what does that mean? That means that I have a fairly simple Markov chain. Yes?
What is the number 2k?
We will come that to, because the target phase has no weight. So again, it's a Markov chain. If I give you which edge I want to peel, so it's a Markov chain, so I condition on what is the exploration up to time n, then I have some edge to explore, and I tell you I've got 3 possibilities for my events. And what are the possible transitions for those events? So either I discover a new phase, which is not the target phase with this probability, or I split the whole into 2 guys, one part is filled with this probability, or I discover the target phase with this probability. So here, the same for the role of the target. The target is on the left or on the right. And I need to tell you your question. I need to tell you what happens to the field part. And in this case, so conditionally on event g star k happening, what is inside the boundary of size 2k, in this case, the field in part of perimeter 2k is just a vanilla, a pk Boltzmann map without target. All right? Yes?
So should the probability measure have a subscription of p instead of q?
Here. Yes, you're right.
Also at the top of the board.
Yes. Thanks. I'm dyslexic, you know, left and right, P and Q. Other P and Qs? No? Okay. So I'm not going to do the proof because the proof is exactly the same as yesterday. And I leave it as an exercise, and if you don't know how to do it, we will do this during the exercise session. Exactly the same as yesterday, it's just counting. Just, you want this event to happen, then you force the scenario imposed by your transition, and then you compute, and it's a ratio of these partition functions. Okay? All right. Now, once you have done this, let me make a remark. The remark is that on lecture 2, so it's a very, very simple Markov chain, right? I give you a transition, and when the hole you're exploring is split into 2, I tell you how to fill the part that you will not explore anymore. I tell you to fill it with an independent Boltzmann map. So let's focus on the evolution of the half perimeter of the distinguished hole during this exploration. Okay? So what is equal E0, this half perimeter? What is it equal to at step is equal to 0? Step I is equal to 0. L. Because you start, remember the map that was here, you start from the external face, so you're in a big room of size 2L. Okay? And then from this transition, what you see? You see that the probability that E star n plus 1 is equal to m plus k, knowing that the hole you're exploring at step n is equal to m. What is it equal to? So either the perimeter could increase. The perimeter could increase if you are facing an event of type ck. Okay? These events of type ck, they make your half perimeter increase. So it increases by k if the face you discover has boundary size 2k plus 2. Okay, so this guy is actually, the probability of this guy is actually this one with k is equal to k plus 1. So qk plus 1, wp of exactly what you want, m plus k, that's a new guy, divided by wp of m. Do we agree? So that's if k is non-negative. Or the perimeter can decrease. The perimeter can decrease if I split my hole into 2 parts. Okay? And if I split in a part leaving k on the left or k on the right, the half perimeter decreases actually by k, the part that has been left on the side, plus 1 because I have glued 2 edges. So this decrease if k is positive, if minus k is strictly less than minus 1, this decreases of minus k with probability, which is w k minus 1, and then the ratio of my partition function with a target. But there is a factor 2 here, meaning that I can lose some perimeter either on the left or on the right.
Okay, so of course in this case, what you mean is it's probability that it is m minus k, knowing that everything.
Yeah, I should put minus k here. You're right with my notation.
And then also.
And the k here is positive. No, that's not so correct. Okay, sorry. Let me be rigorous. Here it's a minus k, and here m plus k. But k is negative.
And it's less than 0.
And that's p here. We will manage it. Yeah, it's a iteration of you converge to the fixed point after some iteration. Okay, but there is also the probability that I discover the target face. And here I will need a convention. It may seem strange at first glance, but actually, if I discover, that's a convention, if I discover the target face, if I discover, or if you discover the target face,
You are not aligned.
yeah, but you can see on the board. If you discover the target face, then the half perimeter, by convention, I will say it drops to minus p. Okay, to minus p. That's my convention. Okay, now if you look at this and you remember what we did in lecture 2, we computed those numbers, WLP. And we had an exact expression for them as follows. So again, that's a test for Alzheimer's disease for me. Where I remind you that ZQ is the fixed point of the function FQ, which was defined in terms of this weight sequence Q. Okay? So as usual, I will put a 4 to the minus L here, a 4 to the minus P here, and a 4 to the L plus P here. And this guy, I will write CQ to the L plus P. This captures the exponential part of these guys.
Two dyslexic typos for L plus Q instead of L plus P. At the right of the formula you have just been writing.
That's my usual dyslexic mistake. But that's not this one. This one is truly a Q. That's funny, yeah, indeed. Okay, and let me call this function, which depends only on L and P, let me call it H, down arrow, P, L. It's a pretty simple function. Okay? So if you plug this into this formula, you see that this is actually equal to, okay, I spare you, I go a little quick, but I spare you some calculation. This is equal to that. This is equal to 2W minus K minus 1. How much do I drop? I drop C to the K. And I also have my ratio of functions. Watch for the dyslexic mistake. And also, with my convention, it turns out that if I discover the target face, so this happens with probability W M. What is my target? Okay, here I'm under P L P, so it's M plus P minus 1 without target here, divided by Wm with the target P. And it turns out that this function is also equal to Q what? Q M plus P minus 1, this guy, CQ, no, it's a minus, sorry. It's W, what do I need? I need to go from M to minus P, right? Huh? So it's M P minus 1, CQ and what did I say? From m to minus p. So my drop is m plus p with a minus. H of minus p divided by h of m. I claim that this is the same if, convention, if you put this guy to be equal to 1. Because in this formula was holding for L and P bigger than 1. Okay? And so my convention is I put HP down arrow of minus P is equal to 1. Believe me, that's just calculation with what it is, and I need a 2 here. Sorry, to be exactly the same as this one. It should be, yes. So that's just playing with the formula. And for the probabilists in the room, you should recognize something here. So these are transition functions for a Markov chain, because the half perimeter is a Markov chain. And the transition for this Markov chain have a very particular form. They are expressed by something here, and then the ratio of a function that depends only on the perimeter. That's the perimeter you start with, and that's the perimeter where you arrive. Perimeter you start with, perimeter where you arrive, perimeter where you start with, perimeter where you arrive. Okay? And that's an instance of what is called a Doob H transform of a Markov chain, which I will now remind you of the basics of. Okay, so what is a Doob H transform? Yep.
I don't understand why the 2 on the last line.
Because you got a half here.
You compare with your expression.
It should be okay, because this one, if you compare with which expression?
With the ratio of the values.
This one?
Yeah, but just pretend that you could fix h of something equal to 2.
True. No, you're right. But let me correct it. Thanks. You're right. But it does not change anything when you have a ratio of h's where n and p are bigger than 1, but it does affect this case. Or, I could have tricked the other way around by putting this value half, or 2, or whatever I need to put it to be correct at this transition. Okay, so what is the basic about H transform of Markov chain? So assume you've got a Markov chain, transition functions here, that's transitions of a Markov chain. On a state space omega. Okay, that's your state space omega. And assume you've got sorry? Yeah, discrete. Everything is discrete here, but that's working in the general case as well. So assume you've got a part in your omega, which I denote A, and think of it as the symmetry. Okay? Blah, blah, blah. And assume that you've got a function h, which is defined on omega, takes values in R plus, such that h is positive on the complement of A. So h is positive here, and that h is harmonic on the complement of A. So h is harmonic here, hence the name h. That's for Remy. So what does that mean, being harmonic in this? Meaning that if you put a point x here, if you take x not in A, you compute the value of h at x. It's the same as if you were averaging over all y in omega of the value of h at y times the probability that you jump from x to y. Okay, so if you are in this setup, I claim that you can define a new transition, qxy, transitions. So they are transitions from the complement of A to omega by the following formula. Q of xy is just equal to the former transition P of xy, but you change it, you modify it with this harmonic function by putting the harmonic function where you arrive, h of y, divided by the harmonic function where you start with, h of x. Okay, that's for all x not in A, and y could be in omega. So I claim it's just a transition function, y. If you fix x and you sum over y, you want to see that the sum of this guy is 1. But if you sum this guy over y, you put the h here, and it's exactly this guy. Right? So it is indeed a transition probability if you fix x not in A. All right? And so what do you see when you do such a transform? You can consider the chain. You can consider the chain that starts from some x here, follows the transition q, follows the transition q, follows the transition q, until you enter A. If you enter A, your transition is not defined anymore, and so you stop. Okay, so you can define the process started in A complement, following transition Q, and stopped when entering A. And this process is called the doob. I will drop the doob soon. The H transform of P. Okay? And your starting point, x0, can be whatever. And it's very easy to check that for this new process, call it, okay, what is the probability that you end up at some particular point after n steps? So if you fix x0, x1, xn minus 1 not in A, and xn can be wherever, what is the probability that you follow, Q, that you follow those transitions? That is, you start with x0 and you end up at xn. It's very easy by this formula to see that you have a telescopic product, and you will get the initial weights for your chain, just modified by the ending point, h of the ending point divided by h of x0. Okay? Very simple from this position. And so remark, in particular, if your function h, if your harmonic function h is equal to 0 on A, what can you tell? That might be the case. It's not mandatory, but that can be the case that your harmonic function is actually null, 0 on A. You will never enter A, because if xn is in A, this is equal to 0. Right? So if your harmonic function is null on A, the H transform never enters A. Okay? And so we can think of this chain as the initial chain condition not to enter A. And we'll justify this in a minute. Okay, so when we come back here on this formula, you want to see this machinery here. And so you want to say that this perimeter process, so that's the perimeter, the half perimeter of the unique hole in a field in exploration, has a H transform of something. What is this something? This something is just this guy here. And so this is what I introduced last time. Definition, nu defined by nu of k being qk plus 1 cq to the k for k bigger than 0, and nu of minus k being equal to w 2 k minus 1 cq of minus k for k less than minus k for k larger than 1, because it's a minus. This defines a probability measure on Z. So it's a definition and actually also a proposition, which I'm not going to prove. You have to believe me that it is actually a probability measure on Z. There is at least 3 proofs of it in the lecture notes. Believe me. It's very easy to see by taking limits. In when m goes to infinity, it is actually a sub-probability measure. The fact that it sums to 1 is a bit more complicated, but believe. So what do we see here? We see that these are the transitions of the new random walk on Z. It's just the transition of the new random walk on Z, because the new random walk on Z jumps from m to m plus k with exactly those weights, right? And so let me put it here. Proposition. We are exactly in the setup of H transforms here. And proposition. So the process of the half perimeter of the unique hole in a field in exploration under this measure PLP is the HP down arrow blap transform of the new random walk on Z started from L and killed when entering Z less than or equal to 0. In particular, what is this guy, HP down arrow of L? This guy is nothing but just the probability that under this random walk, when you start from L, so in the notes it's mat BF to distinguish with the mat BB. It's just the probability that when you enter the negative part, you enter it actually at minus P. So what does that mean? That's the probability that your walk started from L, that's minus P here, does something like that, and when it enters this half space, it enters by jumping exactly at minus P here. Okay? And so corollary, if you wish, hence, this process has the law of the new random walk conditioned to die at minus P when becoming negative, non-positive. Okay? So this statement is almost trivial from what we have. Let me see if I'm doing it or not. Yes, let me do it. Just to practice a little bit H transforms. Who wants to see it? Who doesn't want to see it? Okay, so Rémi is a dictator. You won't see it? No, I'm kidding. So proof. Yep.
So the fact that the mu is a probability measure, when we think about how it arose as limit, then this means that when we when we cut a hole into two, typically one of the two holes will be a
Exactly.
1. Right?
Yes. Yes.
So is there an intuitive explanation for that?
Computations.
Okay.
And okay, let me tell you why. But that will be cryptic. Cryptic. Proof. Look, that's one proof. There are others. Proof. So what do we know? So these guys, they tell you that the transition, okay, let me write this as the transitions. So this was nu of k, nu of k, and nu of k. Okay, so the transition, let me erase those. So the transitions, these are the transitions for this process, the perimeter process, and this is my random walk. So what do I know? This shows that actually this function hp down arrow is harmonic on z positive for the walk, for the new walk. Why? Because look at this, this is just hp of L, let me put an L here, or M if you wish. M, that's the sum of the new k of hp m plus k, and here you sum for all k in z. And m here is bigger than 1, so it's exactly harmonicity of the function hp for the walk on the positive side. Okay, so you can write with the optional stopping theorem for martingale, yes? Yes, yes. If P, L are negative, I put it 0 unless P is equal to minus L. Or if you prefer, HP of minus P is 1. That's the only case. So if you, and believe me, this is done so that everything works smoothly. So if you, okay, it's harmonic. Let me, I'm going too fast here. So if Sn is a new random walk, then you know that HP of Sn is a martingale. Actually, not quite. You need to kill the walk when it enters the negative half line, because the guy is harmonic only on the positive side. Okay, so you write the optional stopping theorem, which tells you that HP of L is equal to the expectation of your martingale at any time. So HP down arrow of Sn inf tau z. Okay? And now you want to let n go to infinity. And you notice that this function is bounded. Why? Because HP of L is roughly 1 over square root. It's roughly L over L plus P, 1 over square root L, 1 over square root P. So if P is fixed, when L going to infinity, this function is actually going to 0 to infinity. There is a constant here. Well, the meaning of approx is up to constant. Right, so you can let n go to infinity, and this guy will converge to what? This guy will converge towards, well, the stopping time, tau at the stopping time. But if you don't reach the negative half line, that means that you are going away to infinity, and so your h tends to 0. So let me put it here. Indicator that you actually enter the negative half line. Okay? And what is this? Well, with what Jean-François made me recall you, this guy is actually 0 unless you enter the negative half line exactly at minus p. So that's the probability that when you start from L, you enter the negative half line exactly at minus p. All right? So that proves this part. And now, why can I interpret this guy as the walk, the standard new walk condition on this event of, that's an event of positive probability, right? So I can condition something on an event of positive probability. And what do I get? So now take any path starting from L and ending at minus p as wanted. Okay? Any path. What is the probability that we see this path for the H transform? It's the formula I erased here. This is just the probability that we see this path for the new walk times the ratio of the H transform at the ending point divided by the starting point. So HP of minus P divided by HP of L. Okay. So this guy is 1. And this guy is just the probability that blah, 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 you enter the negative half line at minus p. So I'm exactly showing that the probability to see something under this measure is the probability to see the other thing under the walk divided by this probability. So if I were to condition this on this event, I would get it. Okay? So that proves this part. Woo! Those who have seen H transform should think that I'm going slowly and so on. Those who haven't seen H transform should be terrified. Am I correct? Yeah. Probably for the second part. Even for the first part, am I going fast as well? So this was to get you accustomed with H transform, and it's not supposed to work. You should not get accustomed to H transform now. You should be still terrified. Are you? Okay, so now, you see, I'm a really good teacher. So now, we will do a parenthesis, intermezzo. We will do an intermezzo. And we'll look at H transformations of vanilla random walk on Z. And we'll see what we can do. Okay? Before that, I need you to swallow one leap of faith. This works. I have done the proof here for L and P larger than 1, because this was the size of my boundary face and target face. This also works for P is equal to 0. What is the target face of perimeter 0? For those who have seen the lecture notes, it's actually a vertex. So it has an interpretation. But here, just believe me, this HP has a well-defined meaning when P is equal to 0, and this works well also for P is equal to 0. So it's a leap of faith. I ask you to believe me. Okay, forget about planar maps. And now I'm a master teacher in Master 2 in probability in Orsay. So let nu be a non-trivial probability measure, non-trivial on Z, meaning that it's not concentrated on one point, it's not concentrated on the positive half line, nor on the negative half line. It's really something. Okay? And we'll also suppose it's aperiodic in case I need it. Okay, so you can consider Sn new random walk. So what is a new random walk? It's just the random walk on Z with independent increments with this law. Okay? So far so good? Are we good, as would El-Hanan say? Are we good? So, proposition. The behavior of a one-dimensional random walk can be classified into two things, which you know, transience and recurrence. But that's for the Markov chain perspective. For the random walk perspective, it's categorized into three categories. So, one of the following holds true. Exactly one holds true. So either your walk tends to plus infinity almost surely. We say it drifts to plus infinity. Or your walk drifts to minus infinity. Or your walk oscillates. What does that mean? That means that you will reach arbitrarily negative value, and you will reach arbitrarily arbitrarily large positive values. And everything holds almost surely. Okay, that's very simple, because if you're not in one of these three cases, that means that your random walk stays bounded in some width of bounded size. It's not possible for random walk, which is not trivial, right? Because at each step you can do crazy thing and escape from your width. Okay, so our question will be how to condition such a one-dimensional random walk to stay positive. How can I define the random walk Sn condition to stay positive for all n? So there is a simple answer. Well, if you random walk drift towards plus infinity, then there is a positive probability that you actually stay positive forever, non-negative forever. Right? Is that clear? If you start from 0 and you know that there is a positive probability that you go to plus infinity, that almost surely you go to plus infinity, then there is a positive probability that actually you stay above 0 for all time. Okay, so if Sn drifts towards plus infinity, then the probability that Sn is positive for all time is actually positive, and so you can condition on an event of positive probability. So you're fine. But on the other case, you say, yeah, but that's an event of 0 probability, because if your limit is minus infinity, almost surely, then that means that this is a conditioning on a 0 probability event. It's even worse if you know that you want to go to minus infinity. All right. So what's the remedy? C'est ça, remède? Yeah. It's to go through a bit of fluctuation theory of random walk and what is called the renewal function. All right. I'm lagging as usual, but we'll see. Okay, so the renewal function. If it seems like black magic, It's normal. So introduce the function h down arrow of L, which a priori has nothing to do with the function, but of course it's the same. That's the probability that my walk, when I started from 0, my new walk, here you've got minus L. That's the probability that when my walk does something like this, the first time it enters this part, it enters it exactly here. Okay, so that's the probability that the hitting time of z less than minus L appears exactly at minus L, and this guy is finite. That's the probability to enter this half space exactly at L. Right? That's a function. And it's easy to see that this function is harmonic. Then we claim that HL, this function, H dot, is harmonic for the walk on Z strictly positive. Why? So that's for L larger than 0. So what is H? Let's see if you have understood. What is H down arrow of 0? That's the probability that the first time I'm in the negative, I'm at 0. Yes, but at time 0, I am at 0. So H down arrow of 0 is? Yes, but if you're the only one to follow, then... Right? L is equal to 0. At time I is equal to 0, you are on the negative half line, and so this is 1. So I claim that H is harmonic for the function on Z, on the strictly positive half line. Why? Well, okay, let's write. What is H of L for L larger than 1? So what is this? This is the probability. So let me do a drawing. That's the probability that you've got your minus L here. That's the probability that when you start here, the first time you enter this half space is actually via the top. Okay, that's this probability. What do? You say, but I can do one step of the walk first, see where I am, and then ask what is the probability to enter this guy after one step. So it's exactly the probability that, okay, here you start from L. It's exactly the probability when you start from L plus x1, from 0, start from x1, that, the same thing. That's just Markov property. But when you start from x1, this is exactly the same as if you were shifting your axis here. You put 0, and this height becomes not L, but L plus x1. Right? And so this is exactly equal to P of 0 of H down arrow of L plus x1. Yes. Yes?
Expected value.
Yes, here I'm an expected value here. Yes, thanks. Notice that if I do a negative jump, which takes me below minus L, then in the argument of the function h, I will have something negative, which will be 0 by this. So h of minus L when L is positive is bigger than 1. That's 0. So it's actually contained here. Okay, so this guy, very simple, is a harmonic function. It's a harmonic function, and actually, it's the kind of harmonic function I was considering here. It's exactly probability. That's why I asked you to believe in this when p is equal to 0. Because when p is equal to 0, here I was starting from L and asking when I'm entering the negative half line. And there I was starting from 0 and asking when I'm entering below minus L, which is the same up to a shift. So that's exactly this function I was having here. Okay? Okay, but remember, we want to condition the walk to stay positive. This function has the nice property that we've got our set A, which is, you know, a tête de mort. We don't want to get here. We don't want to get here. And so we want to find a harmonic function which is equal to 0 here and which is harmonic here. This guy seems to do the job, right? It is harmonic here and 0 there. Not quite. Not quite, because exactly here, the function here is equal to 1. So it's not quite a harmonic function which is negative on the 0 on the negative half line. Okay, so we will trick this by introducing the renewal function now. So what is a renewal function? I go slower in a master course in Orsay, don't worry. So the renewal function is just the discrete primitive of this function here. So you introduce h up arrow of L. Now the discrete primitive. So it's h of 0 plus blah, 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 plus h down arrow of L. So that's for L bigger than 0. So what do you know? You know that h up arrow of 0 is 1 by this, and h up arrow of what? H up arrow of minus L, when L is larger than 1, is 0. So it's negative on the strictly negative half line. Right? Let me give you an interpretation of this. So what is h of L? So that's the sum for k is equal to 0 to L of the probability that you walk started from 0, touches this part of the board exactly at minus L, at minus k. Okay, so now I need you to concentrate. Just now, the rest of the lecture was okay. That's the expectation of, what do you do? What is this for the walk? This, think in terms of sport. This is a negative record for your walk because it has never reached that part before. So it's the first time you reach that part. And so I'm asking whether the negative record, the first negative record below minus k, occurs precisely at minus k. So now if I sum over k from 0 to L, then this h of L is just the expectation of number of minimal records in 0, minus 1, up to minus L. So let me do it with a picture. It's the number of okay, that's your walk, that's your threshold minus L, and you count the number of records, of minimal records. That's a new record, that's a new one, that's a new one, a new one, a new one, and then this one is not in between 0 and minus L. So that's the number of red points here. expectation number of red points here. Right? All right. And now proposition. This function is very nice. It's called the renewal function. I'm stealing one more chalk, Philippe. Thanks. So theorem, even. Theorem. So this renewal function is bounded if only if and only if the walk drifts towards plus infinity. And actually, H is superharmonic on the non-negative, always, and harmonic if only if Sn does not drift to minus infinity. Okay, theorem. Let me prove this theorem. Do not worry too much, because this afternoon in the exercise session, we'll do examples of this. Hint for the simple symmetric random walk on Z. We'll see what it does. And it's not, I mean, you can follow the next lecture if you have not understood the whole picture there. So proof. So what is? Let's start with this. And let me accelerate a little more. What is this? This is the expected number of records I have in 0 minus L. So that's obviously increasing in L. Okay, so if H is bounded, that means that the expected number of minimal records at all is finite. And so if I have a finite number of minimal records, I have a finite number of minimal records almost surely. So this guy is finite almost surely. But yes, but so far I'm, this sign. But almost, you'll see. Where was I? This guy is finite almost surely. And so I claim that if you have a finite number of minimal records, that means that you must drift towards plus infinity. Because otherwise, you will get to arbitrarily large negative values. So you will make as many minimal records as you wish. Okay, so this implies that Sn drifts towards infinity. Haha. As Rémi was pointing out, if we want to go the reverse arrow, if Sn drifts towards infinity, then truly we will have a finite number of minimal records, and so the expectation is finite. And so this guy is bounded. Why? It's not a bottle of champagne or wine. Because this guy, the number of records, has a geometric distribution. Once you're a record, I'm the new, comment il s'appelait, the runner, the guy? Bolt. I'm the new Bolt. I run, that's my new record. Okay, it's not true for sport, but by the Markov property here, I can reset everything, put my x's here, and the number of records I will get after is independent of what I got. So this guy actually has a geometric distribution. And so for a geometric distribution, being almost really finite is equivalent to having a finite expectation. That's true for geometric. All right, so this is done. This I like very much because you will not understand anything. But that's so beautiful. Okay. Do I have time?
10 minutes.
Yes. So it will use one super nice fact called duality. So what was Philippe saying about duality? It's something all around in mathematics with different names. So there, the duality will just be this. Okay, so let's prove that H is superharmonic. So we know that this guy is harmonic on Z strictly positive. So I know that H of 1 is nu of k, H down arrow of 1 plus k, blah, 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 up to H down arrow of L is sum of nu of k, H down arrow of L plus k. Hint, do not take notes. This is verbatim in the lecture notes. And try to follow. Let me sum this. I sum. So if I sum, what do I get? I get exactly the renewal function minus the one at 0. So renewal function at L minus the renewal function at 0, which is missing here. And what do I get on the right-hand side? Nu of k. And the renewal function at L plus k minus the renewal function at k, because that's the one missing. All right? So what do I see? I see that I almost have what I want. H of L is the sum of nu of H down arrow, upper row of L plus k, provided that I have harmonicity of H exactly at 0, meaning that H of 0 is this nu of k, H upper row of k. Okay? If I have harmonicity at 0, I then use harmonicity at any L. Okay? And it will follow from the proof that if we don't have this, it's in the good direction so that it's superharmonic. So let's look at this. Let's look at this. Let's look at this. Where? Okay, there. What is H of 0? H of 0, we know what it is. It's 1. And what is the other guy? The other guy is sum of nu of k, H up arrow of k. Here I was summing over k in Z, but clearly this guy is negative, is 0, sorry, if k is negative, so I can restrict for k positive. Let's write what it is. So it's nu of k. What is H up arrow of k? That's the expectation of number of records in 0 minus k. Right? Okay. So let's see what is a record. So I sum over all k. What is a record? I am a record in between 0 and minus k if I am a record at some I in between 1 and k for some time n. What do I mean I am a record? That's the probability that my walk started from 0. There is some minus I here, which is larger than minus k and less than 0, such that my walk has some record exactly at minus I. You agree? Because the sum of the records the expectation of the number of records is the sum of records in 0 minus k. I fix a minus I in between 0 and k, and I do sum, and I fix here time n, and I know it appears at some time n. It's just decomposing this event. And now I do what I promised to do. I do this. Meaning I'm considering this as my new coordinates. What is this process? I claim that this process exactly has the law of my initial random walk, because here you have a negative steps. If you look like this, you see a negative steps. All right? So let's do like this. What do we see for the walk? The walk starts here, stays strictly negative, and ends up at minus I. So that's the probability that my walk is strictly negative. No, okay, because it could be 0. Okay, let's say negative. And that Sn is equal to minus I for the first time. Yep, okay. There is some slight point. Let's. Okay, I don't want to. Yeah. Okay, but what is this? So that's the probability that my walk. Let's write as a picture in the good direction. That's the probability that you are something like this at minus I. Let's use this guy now. That's at time n. If I use this guy, that's the probability to see that, and I can add a new step of minus k. Minus k is of k, sorry. So adding this guy inside the probability here makes me a new step for the walk. So if I'm putting this here, this is equal, the whole thing here is equal to the sum of the whole n of the probability that my walk does this. And what is this? This is exactly coming back to this part at time n. So that's the probability that my first return in z positive, that's the return time, so let me put a star, it may not be 0, appears at time n. So if I sum over n, that's just the probability that my walk, Sn, comes back to z. And what is the probability that the walk comes back to the positive half line? It's just the probability that the walk does not drift towards minus infinity. Because if you either oscillate or drift towards plus infinity, this is equal to 1. So this is 1 if only if S does not drift to minus infinity. And otherwise this quantity is strictly less than 1. Hence, this guy is superharmonic. All right, how much time do I have? 1 minute? Can I steal 1 minute? I was starting 2 minutes late. All right, so what to do with this renewal function now? What to do with this renewal function? That's the question I'm asking you. So we have a walk that does not drift towards minus infinity. So let's say it oscillates or it drifts towards plus infinity. And we have a function, h, which we build out of the walk, this renewal function. We have a function that is harmonic on z larger or equal to 0. So h is harmonic on z larger than or equal to 0. And h is equal to 0 on the complementary. That was not the case for h down arrow, because h down arrow was indeed 0 there, but was harmonic on this guy. Not quite the complementary. Huh? You agree? So we can perform a H transform. So we will denote by S up arrow n the process, the H transform, the H up arrow transform of this walk Sn by this function H, the H transform by H up arrow. Okay? All right. And so what do we know? This guy will be a Markov chain. This will be a Markov chain starting from, say, 0 or 1 or 2 or whatever. But we know that this Markov chain will never enter this part. It's a Markov chain that will do something like that. And we want to say, and actually there are very good reasons, you can look in the lecture notes. There are very good reasons to call this process the walk S condition not to hit the negative half line, in the sense that it is a limit of the walk condition not to hit this guy for time n and letting n go to infinity. So we'll see that this afternoon for the simple symmetric random walk. All right, so let me make a teasing now of what we are doing next time. So what we're doing next time is we have this perimeter process under this target measure, which is a HP down arrow transform of the new random walk. So our goal will be to define infinite maps now. And we will see two ways to define these infinite maps. One is more trivial than the other. The first one will say, okay, imagine that we let L go to infinity and we fix P. P is a target face of perimeter 4, but we start with a boundary which is gigantic. And we will see that this guy, the ratio of this H transform, will disappear in the limit when L goes to infinity. And so we'll see that this guy in the limit converge just to the new random walk. And this new random walk will be associated to defining a half-planar map, a map of the half-plane, with an infinite boundary on your right, so L is equal to infinity. Then we'll do a second conditioning. So P fixed. Then we'll say, oh, now L is fixed. And we'll let P go to infinity. And in this regime, we'll see that this HP down arrow transform turns out to be a H transform. Just by, just take this function, let P go to infinity, and see what the function you get. Aha! H transform and H transform, so we will get that this perimeter process will have the law of this random walk, condition to stay positive. And from this, we will associate the geometric object, which is an infinite planar map with, you've got your boundary of size 2L, which is fixed, but then your map will be infinite. Not the same as this one. Here it's infinite here. There, the boundary is finite. Okay? And we will also ask the question, so we'll see what time we will get at the end, because this was supposed to be today. We'll also, what if my random walk S here is actually drifting towards minus infinity? So this theorem with the H transform collapses. I have a walk that wants to go to minus infinity, and I want it to go to plus infinity. Who will win? So we'll see that. Maybe I'll let you guess. We'll see that in the probably the lecture somewhere next week, and we'll see that this is related to hyperbolic type of random maps. Thanks.